So for the AAC block, the density for the AAC block, the density of the AAC block is almost 10 kilometer per meter cube. For brick wall, it is 19 kilometer per meter cube, and for concrete wall, it is 24 kilometer per meter cube. Okay, so generally we use in the residential building AAC block in the brickwork, and like I will tell you in like different lectures why we use concrete walls. So we use concrete walls to give the additional strength to the buildings, but basically for the high-rise building we use concrete walls to give the additional strength to the building, but not in the like low-rise building we use concrete wall. Okay, so this is our residential drawing for the G+3 building. Okay, so here we use I think we use the brickwork only. Okay, so to see, here you can see there are different width of the walls we use in the we are using in the building. Okay, so so what we will do, we will check the dimension of the each wall. So this is 230. Okay, and it's also 230 here. It's also 230, and here it is I think 100. Okay, it's 115. So 115 is there, and it's 230 wall width is there, and it's also 115. Okay, so what we will do, we will print this and we will make a PDF of this drawing, and for that you have to press Control P, go to the previous plot. Okay, and click on window and select the window. Okay, and select the portion in which you have to create the PDF, and click on the preview and click plot, and now the PDF generated. Okay, you can save it. Let's save it on the desktop. PDF and save. Okay, so let's open the PDF. Okay, so what we will do, we will mark the 230 and 115 walls for the better I think for better view. Okay, so for better selection, we can select these walls in our ETAB, and we can assign the wall load over there. So what we will do, we will go to the comment and pencil. Okay, so what we will do, we will mark to this one minute. Okay, so this one and this one is there, it's 230. We will mark the 230 wall. Okay, this wall is 230, this wall is also 230, this is 230, and this is also 230, and here this wall is 230. Okay, let's use different color. Okay, because there is a lot of red color is there in the, so what we will do, we will choose the color, we'll choose purple color. Okay, and let's take it full. Okay, now we can proceed. So this is 230, this is also 230, here is 230, here is also 230, okay. And this wall is 230, this is 230, okay, and this wall is also 230, 230. It's also thickness, the width of the wall is 230, 230, okay. This is also 230, 230, it's also 230, 230, okay, this also 230, and here it's also 230, okay. No, no, it's not 230 here, okay, fine. It's ground floor, right? Uh, 230 is here, okay. This is also 230, 230, 230, 230. It's 230, 230, 230, 230, and it's also 230, 230 here. Okay, this is not 230, okay. And now we will select 115 width thickness walls. So let's go to the pencil and we will select now green color, and this is 115. Okay, so I think again we have to select this. This is 115, 115, 115 is here, 115 is here. Okay, this is also 115, 115 is here. Okay, and this is 115, 115, 115. This is also 115. It's 115 here, 115 here. Okay, this is also 115 here. So that you can mark as per your convenience. Okay, we will open the ETABS model. So this is the section of the building. Okay, so here you can see. So first we will select. First we will. So first we will give the input to the Excel. What is the width of the wall? So here the width. You can see the wall thickness. Wall thickness is 115, and there is another wall thickness is 230. Okay, and so here the brick, we are using brick wall, so the density is 19, you can take. Okay, and here the plaster thickness, so you can, so if this is wall thickness, so if this is a brick wall, so one side the plaster thickness is 12 mm, so the both side the plaster thickness will be 24. So here that's why we are using plaster thickness 24. Okay, and so okay. 1 minute. Control P, plot window, and let's take a PDF. Preview, plot, save. Control P, plot window, preview, plot, and run and save. So here you can see. So let's take it, come pencil, and so this is a total floor. This is a total floor. It's floor to floor height. Okay, let's take it H, and this is only wall height. Okay, so what we are doing, we are like, so from the total height we are removing the beam depth. Okay, so here you can see we have to give the input to the Excel. What is the beam depth? So here the beam depth is, we have taken beam is, I think it's 450. So give the input to the beam, that is 450 and 450. And what is the total height of the floor to floor? So here we will check what is the total height from floor to floor. So we will go to the our AutoCAD drawing, you can see here the floor to floor thickness is 3.15 from ground floor to first floor, and from first floor level to second floor it is 3150, and from second floor to third floor it's also 3.15 meter, and from third floor to terrace floor it is 3.1. So you can see for ground floor it's 3.15, for first floor it's 3.15, for second floor it's 3.15, but for third floor it's 3.10. Okay, so the calculation will change for the third floor, but for the second floor, first floor and ground floor the wall load will be same. So what we will do, so here we have two height. So what we will do, so let's copy this. 1 minute. Okay, let's copy this at this location. 1 minute. Let's copy this and paste here. Okay, and let's write, it's not better, but okay, let's copy this and paste here. So here we will again 115, we will give the input, the thickness of the wall, and it's 230 here. Okay, and so the total height is 3.1 for the third floor. Okay, and its beam depth is also 450. Okay, and okay, it's a clear height, and its plaster thickness, and its density of the brickwork and opening. Okay, so suppose, so there is a window opening in this wall, but in this wall there is no opening. Okay, so because of the opening, what we will do, we will take 20%. Okay, we can reduce 20% of the wall load for door opening or window opening both. Okay, so what we will do, we will give the input that is 0.2, you can say. Okay, so what we are doing, we are reducing 20%. So we can write 0.2, so that will reduce 20% of the wall load for the door and window opening. Okay, so let's take it 0 right now, and if there is opening we can take 0.2. Okay, or what we can do, we can give the maximum load, like we can apply maximum load to the beams. Okay, or you can calculate accurately and apply to the beam. Both you can do, but always do the conventional design, always take the higher loads. So here is the calculation. Let me give you the calculation. Let me give you the understanding of the calculation for the wall load. Okay, so the formula to calculate the load, okay, wall load is, so density into volume. Okay, let's take it density into volume. So the density is 19 kilonewton per meter cube. Okay, and we will calculate the volume. So this is, so you can see this is floor to floor height, that is h, and this is wall height. So we have to calculate the wall height. So for that, what we will do, we will calculate it h minus actual wall, h minus beam depth. Okay, so beam depth, let's take it d, and we will multiply with the thickness of the wall. So let's suppose thickness is t. Okay, and then we will get the result in kilonewton per meter. Okay, that is UDL load we are applying on the beam. Suppose this is beam. Suppose this is this is our, that is our beam. Okay, and what we are doing, we are applying UDL load on the beam. Okay, and that will be kilonewton per meter. Okay, so give me a minute. So let's calculate the wall load. Wall load equals to density. Density of brickwork is 19. It is in kilonewton per meter cube. Okay, and we will multiply with uh, height. Total height is 3.15 minus depth is 0.45450 mm, or in meter it's 0.45. It is in meter. Okay, it will be in the meter, and we will multiply it with the thickness. Thickness is 230, 0.23. So it will be like 19 kilonewton per meter cube, multiply with 3.15 minus 0.45, and it's 2.7. It is in meter. Multiply with 0.23. It is in meter. So meter, and it will be meter square, and it will cancel with the meter cube. Okay, and our final result will be in the kilonewton per meter. Okay, so let's calculate this, and it will be 19 multiply 2.7 multiply 0.23, and it's 11.799. Okay, it is in kilonewton per meter. Okay, so let's so here what I have done, I have not taken the plaster thickness load. Okay, let's take it 0. So you can see it's 11.8, and in our calculation it is 11.799. Okay, so it is, we are doing correct. So here what we have done, we have taken plaster thickness also, so it will be 13.16. Okay, So let's come to the model. Okay, we will select only 230 wall thickness beams. So that is purple one. We have to select all the purple beam. And now if you if you want to assign the wall load on the building, you have to go to the assign frame load, distributed load. Okay, and here you have to select wall, and let's uh, copy this and paste here and apply. So you can see we can see wall load now. Okay, and like let's see in the 3D. Why it is showing like this? 1 minute. Okay. Copy, select, import physical object. Okay, now it's perfect. So if you want to see the wall load, go to the display, load assign frame, and here you have to select the wall and apply. You can see we have successfully applied the wall load for 230 mm. Okay, and now click here, show on deform shape, and go to the plan, and go to the plinth level and apply. And here, please make sure you have selected all story. Okay, and again go to your your architecture plan, and here you can see the mid one, all the mid one beams At the mid one beam, at the middle beams, every wall thickness is 115. So you have to go to the Excel and select 115 wall thickness load. Copy this and let's select every mid beam here. Okay. So we have selected every middle beam here and we will go to the assign frame load, distributed load, and we will paste the load value. You can see it is in kilonewton per meter and I will apply it. And you have to select the load pattern wall here and we will apply it and okay. So let's open in 3D view. Here you can see we have successfully applied all the wall load. Okay, if you want to see the only plinth level wall load, so what you can do, you can select this perspective toggle. Okay, and you can see here, you can see all the load. Okay, for the plinth level in 3D. And let's go to the plan and select the plinth and okay. So at the terrace level, what we have to do, we have to select the terrace level, apply, okay, and go to the short the undeformed shape and select one story only, and we will select all the beam here, and we will go to the assign, okay, frame load, distributed load, and here what we have to do, we have to check. So what is the thickness of the wall we are using at the terrace level, and we will select the dimension. We will check the dimension and it's 230. Okay, and we have to go to the Excel now again. So for the parapet wall the total height is 1.5, and here we have to give the input to the Excel. What is the thickness of the wall? It's 230. Okay, and it is 6.12 only. So what we will do, we will apply 6.12. So again, 1 minute. So you have to go to the select object type, select beam only, and select beam and show selected object only. Okay, now we are seeing only beam. Select all the beam, go to the assign shell load uniform, and here you to select the wall. No. Go to the assign frame load distributed and select wall and paste and apply. Okay, so here what you can do, you can select the middle beam and you can remove the load from the middle beam. Okay, here you can see it is like this. Or what you can do, let's undo this again. Okay, so it's a terrace level, and please make sure it's one story. Okay, and what we will do, we will select this. Okay, so let's remove this load. Okay, let's remove, because here you have to take the wall load for the above floor. Okay, so what you have to do, you have to select these beams and this beam also, and let's remove the load. Okay, go to the assign frame distributed and here you can delete the existing load and apply. Okay, now what we will do, we will take this one only. So like this. And now we'll assign the load. Okay, go to the assign uh, frame load distributed, and we will apply the parapet wall load. Okay, at the terrace level. So now click 3D, show all object. Okay, and go to the display, load assign frame, and select the wall load and apply. Okay, so you can see the all the wall load now in the detail. Okay, so here you can see. So at the terrace we have applied the parapet wall load, and at below the terrace level we have applied 13.6. Okay, and it's also 13.6. So at this location, so here you can see at the third floor. mm, 1 minute. Uh, so here you can see at the third floor the height of the from third floor to terrace floor, the height of floor to floor is 3.1 only. So we have to take 3.1 total height load here. So we will take 7.13 or 12.92. So what we can do, we can go to the plan and third floor apply. Okay, and here you have to select the show uniform shape. It should be 1 story. Go to the display, load assign frame and wall apply. Okay, so you have to select only 13.61 beam, and you can replace the load with the with 12.92. Okay, so let's select this only. Okay, and I think this one also. So what you can do for the better view, you can go to select object type beam, select, so selected object only. So now you will see the beam only. Okay, here, and let's go to the display option. Option graphic preference. Let's input 1010 apply. Okay, and you can zoom it. So let's select this. Okay, and let's select this also. Let's select this also. This one. Okay, this one also, and let's select this also. Okay, so you can now we will go to the assign frame load distributed load, and we will replace the existing load with 12.92. Copy it and paste here and apply. Okay, here you can see now every load is replaced by 12.92. Okay, now we will select 7.27 beams only, and we will replace it with the 7.13, I think. Okay, copy, and we will paste here and apply. Okay, and okay. So we have replaced every load at the third floor, and at the below load, you can see at the second floor the load is different, and at the third floor the load is different. And now we are doing everything is, so now everything is correct. Okay, so here also at the plan, let's go to the overhead water tank level, and let's take it 1.2 parapet wall here also. So what we will do, we will select, and we will go to the assign shell load uniform. No, go to the assign frame load distributed and select the wall, and we will paste the parapet wall here for 230, and it's copy and paste and apply and OK. And at the below at the mumpty level, you can see, so we have to go to the define, we have to go to the edit stories, modify. So you can see the mumpty level is 3.2 above the terrace level. Okay, and overhead water tank is 2 meter above the mumpty level. So you have to check the calculation every time, okay, what you are doing and why we are doing. Okay, so you have to check the all the loads. So right now I'm not doing it. Okay, let's take it only this one only. Okay, so you have to check every load at the every floor, whether you are selecting the correct load or not for the walls, for the wall only. Okay, so here we have successfully assigned all the wall load on the beam. Okay, so now we will modify the earthquake load as per the IS 1893. So we will go to the R model, select show on deform shape, go to the define, go to load pattern, and here we have to select the EQX and modify the lateral load. And here you can see all the direction eccentricity and all the parameter and the earthquake definition you can see. So what we have to do, we have to untick everything here, and in the x direction we will take x direction plus eccentricity in the earthquake load. And here we have to select the base bottom story, and at the top story we have to select the terrace. Okay, so the response reduction factor, so this response reduction factor we will take from the earthquake code IS 1893. So for that we have to go to the code here, master class, no, not master class, I think code is there. So we have to go to the codes, okay, and Indian, and here we have to search 1893 and open the code, and let's find, go to the find and write response. So here is the response is there, so you have to write response reduction, enter. Okay, so here you can see the table 9 response reduction factor R for the building. Okay, so in this situation, so in this building, you can see in the AutoCAD drawing every, so in we are using only columns here. Okay, so that is moment resisting frame, moment frame system we are using only. Okay, so the our building is located in zone 4. So as per the IS 13920, if building is located in zone 3, 4, 5, you have to design the ductile building as a ductile building. You have to design the moment frame as a ductile frame. Okay, so in this situation, so our building in zone 4, so we have to take RC buildings with spatial moment resisting frame SMRF. So we have to take R5. If our building in zone 2, so we will design it as an ordinary moment resisting frame. Suppose your building in zone 2, so you have to take R is 3 only. So in this situation, so our building in zone 4, it is so daily it is in zone 4, so we have to take a response reduction factor for spatial moment resisting frame. So let's take it 5. So here it is 5. Okay, and seismic zone factor Z. So as per the code we have to take. So let's find the zone factor. So here I have to write only zone factor and search it. So there is a annexer E you can see here. So as per the location, there are many of the zone factor written in the code. Okay, and you just have to find the daily one, and you can see it's a zone 4 and it's 0.24. So you have to select 0.24 here. Okay, so the site type, you have to select the site type as per the geotechnical report. Okay, so for that, so to select the site type, what you can do, let's find out. Okay, so here you can see the soil type or site type, you can say. Okay, and it's 1, 2, or 3. So you can see in the table it's 1, 2, or 3 is there. So as per the soil report, geotechnical report, you have to see the geotechnical report. If your if your n value it's lies in between 10 to 30, you have to take medium or soil stiff soil. So generally your n value lies in between 10 to 30. Let's take it 2 only. So if your n value, okay, if it is lies in it's above 30, you have to take 1, and it's less than 10, you have to take 3 here. So always take it 2 only. Okay, and consult with the geotechnical engineer uh, or your local contractor also for the n value. So let's take it 2 here. And the importance factor. So for the importance factor also, let's find out what is the importance factor in for. So you can see the importance factor table 8 is there. Okay. So you can see there are for the different sectors buildings importance factor is written here. Okay. So our building is so here you can see residential or commercial building other than those listed in SI number 1. So this is serial. It's a SI number 1 is there. Okay, you can see SI number 1 is there. So other than these buildings listed in this one, other than this, you have to take 1.2 with occupancy more than 200%. Okay, so in our case, so it's only G+3 building. So the occupancy is not more than 200%, it's less than 200%. So we have to take all other building, it's one only. Okay, so it's one here. And now we have to calculate the time period. Okay, so for the time period, let's okay, so here you can see the time period calculation for the different buildings here. Okay, so here you can see the time period calculation for the moment resting frame building. It's 0.075 h to the power 0.75. So we have to take this one only. Okay, so suppose in our building there are shear walls is there, so we have to take this also. Okay, suppose column and shear wall is there, so we have to take this. If in our building only shear wall is there, so we have to take the other formula, that is this one. Okay, so you have to take the time period calculation as per the requirement of the projects. Okay, so if in the buildings there are only column, or is there only shear walls or column, or is there only shear walls only, so you have to take the time period calculation as per as per the projects. Okay, we will decide we have to go with which time period calculation. Okay, so here you can see for the steel moment resting frame, you have to take other different time period. Okay, so it depends on the project's material. What is the material selection you have to take? Okay, and it's totally depend on the projects. So by the projects you will get the informations, all the informations. Okay, so let's take it this one 0.075 s to the power 0.75. Okay, so I have made one Excel for that. So let's open this Excel. Okay. Experience. So, I have developed the Excel for the automation of the calculations for the wind load and earthquake load. Okay. So there are some different formula you can see. So at this location, it's the formula is 0.09 H divided by under root D. And okay, and here is the formula is 0.07 to the power 0.07 into H to the power 0.75. Okay. So you just you don't have to calculate everything. You just have to put the building dimensions in x and y direction, and what is the height of the building, and what is the height of the basement and the mumty height. You just have to put uh, these input to the. You have to just give the input to the Excel, and you will get the calculation by yourself only, by itself only, like by the Excel only. Okay. So let's give the input to the Excel. Okay, I will share this Excel to you. Okay, it is not in the master class material. Okay, folder. I will give you the Excel personally only. Okay, so let's go to the model, like ETABS model, and here click OK and click OK, and go to the plan and click terrace. Click on the terrace and apply and OK. So here you can see at the terrace level there is it's 14.55. There is no basement in the section. It's only G+3. So in the Excel, okay, so basement height is 0. Let's take mumty height is 0. So we are taking total height up to terrace, that is 14.55. So let's place 14.55 here. Okay, so in the x direction, in the y direction, we have to check the dimensions of the building. So let's take it from outer column to outer column, from center to center of the column. Okay, so for the dimension, you have to go to the draw dimension line, and you have to click the center to center for the outer columns. Okay, and it's, I think it's 17.045. And in the x direction, the same in the y direction, you have to go to the you have to go to the draw dimension line. Okay, this one, and I think it's this one. Okay, and it's 9.43, so it's 17.045. And in y direction it is 9.43. Okay, so here you can see the T, the frame, the moment resting frame. Okay, so we have to take this we have to calculate this time period. We have to take this time period from the Excel. Okay, it's 0.075 h to the power 0.75. Okay, so let's go to the 1 minute. Let's go to the okay time period calculation section. So here you can see the time period TA. It's only proportional to the height of the building. Okay, so it only depends to the height of the building. Okay, it's not depends on the D. Okay, it's that is base dimension of the building at the plinth level in x and y direction. So it will only depends on the height of the building. Okay, so let's check the height of the building, that is 14.55. And let's go to the calculation. We will calculate it manually also. So 0.075 into 0.075 multiply h to the power 1 minute. So I think it is 14.55 to the power, it's 0.75 multiply with 0.075, it's 0.558. No, there is something wrong is there. Okay, 1 minute. Yeah, I think it's 0.075. 0.75. 0.558. 1 minute. Okay, it's 14. Okay, 14. It's 14.55. So you have to check, in the Excel, you can do mistakes in the Excel. So you have to always cross verify. Okay, whatever you are doing. So it's 0.559. Okay. So in the, I think in calculation we are also getting 0.0559. Okay. So select, copy this, go to the E tab, go to the define section, go to the load pattern, and select EQX, modify the lateral load, and copy this 0.05559 here. Okay, and click OK. So in the EQY section, you have to modify the load, and here you have to untick everything, and you have to take Y direction plus eccentricity in the earthquake, and you have to select terrace here, and response reduction factor 5 here, and it should be 0.24. Soil type should be 2, importance factor should be 1, and it should be user defined. T should be the same one, 0.055 for X and Y direction both. And for EQZ, you have to modify the load. You have to untick everything. You just have to tick the X direction. Okay, and it should be terrace here, 5 here. It should be 0.04, 0.24 here. Soil type should be 1. Importance factor should be 1. And user defined for Z direction should be zero point 0.4. Okay, so I will tell you why we are taking zero point 0.4 here. Okay, and okay, and click OK. So we have successfully assigned the earthquake load. Now we will assign the wind load. Okay, so let's go to the load pattern and click WX and modify the load. Okay, so let's take it 0, and it's a windward coefficient. No, it's zero point 0.1. Let's take it 0.01. Okay, so here there are two methods to calculate the wind load. One is spatial coefficient method and other is force coefficient. So what we are doing, we are uh, taking the force coefficient method. Okay, using the this table. Okay, using the table in the IS 875 part 3. So here you can see we have the, so for the daily, the basic wind speed is 50. Okay, you can see the height of the building is 14.55. Dimension in X direction or Y direction is there. Okay, so we have to calculate the force coefficient for the X direction and the force coefficient for the Y direction both. Okay, so here are the tables to calculate this. So let's go to the 875 part 3 uh, code. Okay, so we will write 875 here. So we will open part 3 with amendment. So this is the IS 875 part 3 for the wind load calculation. You can see. So design load other than earthquake, okay, for building and structures. So 1 minute. You don't need to read all the code. Okay, don't do that. Okay, so I will show you how you can take the all the data from the code. Okay, so here the wind speed is 50 for daily. Okay, so you can take wind speed from the code. I think this is not the one I'm looking for. Let's open this one. I think this one. Okay, yeah, this one is there. So what you can do, you can simply press Control F and write speed. Okay, wind speed. So here you can see the basic wind speed for all the cities and town is here. You can take from that. So in this code that is of 2015, there are many of the amendment happen for the different cities. Okay, so I want to tell you that for Delhi, in code for Delhi it is 47. Okay, but like there is an amendment for Delhi, uh, from Delhi MCD. Okay, so the wind speed increased from 47 to 50 now. So for Delhi, it is 50 now. Okay, you have to take 50. So here we will take 50. The terrain category for Delhi it is 3. Okay, and importance factor. Let's go to the code again. So terrain category depends on the disturbance around the building. For Delhi, the disturbance is high, because that's why we are taken uh, uh, 3 here. Okay, so it depends on the city. So for city location, let's take it 3. Okay, always take it 3, because for the dense area we will take 3 here. So here you can see the manual calculation for the wind, that is Vz equals to Vb K1 K2 K3 K4. Okay, so there are the different factors are there. Okay, so here you can see the K4 is the importance factor for the cyclonic region. So here that is the importance factor here. Okay, so K4 you have to see 6.3.4. Okay, so let's find 6.3.4 and okay. So you can see the importance factor for the cyclonic region. So okay, so you can see here the K4 importance factor. So our building is not industrial structure. It's not hospital, school. Okay, so don't take cyclone factor in your building. Okay, let's take it for all other structure. It should be 1. Okay, so here you can see you have to select 1 here. Okay, it's like it is 1.15 here, 1.3 is there. You can see 1.15, 1.3 is there. You don't have to take that, just take 1 here. Okay, so here you can see now there is a risk coefficient, K1 factor is there. So K1 is a probability factor and a risk coefficient. You have to see 6.3.1. So let's find out 6.3.1 here. Okay, so that is a risk coefficient for different class of the structure in the different wind zone speed. Okay, so here you can see for the all general building for the design life of 50 year, here for all the basic wind speed it is 1. Okay, so you have to take it 1 here. And topography factor. Okay, let's find out the topography factor. Okay, so here you can see the topography factor. You have to see 6.3.3. Control F 6.3.3. Let's find out. So here you can see the topography factor is there. Okay. So there is a clause 6.3.3.1. The effect of topography shall be significantly at site when the upwind slope theta is more than about 3 degree. So suppose suppose this is our building. Okay, and here the slope of the ground is. So the slope of the ground is greater than 3. Suppose this slope is greater than 3. Okay, if this slope is greater than 3. Okay, so then we have to take the topography factor in the account. Okay, So here in our building, this factor, this degree is 0. Okay, there is no slope in the ground. So let's come to our code again. Okay, so it is saying, so below that the value k3 may be taken to be equal to 1. The value of k3 is confined in the range of 1 to 1.36 for the slope more than 3. Okay, so you have to do the interpolation for that. Okay, so in our case it is 1 only, so you have to take 1. Okay, 1 here. So the moral of the story, so you have to take importance factor, risk coefficient, topography always 1. Okay, take it always 1. Okay, if there is a slope, so you have to calculate it again. I think there won't be any slope area. Okay, like you have to, I think you will design building for the flat sections only. Okay, not for the hill area, for the flat ground only. Okay, so always take it 1. And terrain category, if you are designing building for city only, so you have to take 3. Okay, let's like you are designing building for Patna, for Delhi, for Mumbai, for Pune. Okay, for Jaipur you have to take 3 only. So select top story here, overhead water tank, include parapet wall of 1.2 meter. And now we have to calculate windward coefficient. Okay, so here we are calculating using force coefficient method. Okay, so let's go to, I think, uh, let's go to code again. Okay, okay. So this is the table. Okay, this is the table. I think the table number is figure 4. Okay, so this is a figure 4, the coefficient for the rectangular building in uniform flow. Okay, so we have to collect the CF. We have to calculate the CF, that is force coefficient. Okay, value of CF we have to take from these two graphs. Okay, and you can see here. So I think let's take a screenshot. So if building, suppose this is A and this is B. Okay, so this is, suppose, is equals to X and is equals to Y. Okay, this is a dimension in building dimension X and Y direction, and wind is in this direction. Okay, this is in X direction. This wind is in X direction now. Okay, so you have to calculate CF for X. Okay, CF X we will calculate. So first we have to calculate A by B. Okay, and now we will calculate H by B here. Okay, and so these two things we have to calculate. Here you can see H by B is there, and A by B we have to calculate. Okay, this is H by B and this is A by B. So you don't have to calculate this by yourself. Okay, like I think I have already calculated in the Excel. You can see A by B is there and H by B is there. Okay, so X direction, X, it is 17 point. I think it's, let's, okay, calculate. Okay, always calculate. Always click on the OK only. Okay, if you want to close it. So you can see it's 17.045. So it's 17.045, and for y it is 9.43. Okay, or h is equals to 14.55. Okay, so h is 14.55, a is there, b is there. Okay, so you can calculate h by b or a by b. Okay, for x direction. For y direction the calculation will be different. Okay, so you can see it's in x direction, it is a and this is b. Okay, so I think, okay, so you can see a by b is 1.808 and h by b is 1.453. So a by b here you can see, let's remove it. Okay, so you have to take this one, this line, and put here a by b 1.8. So it's 1.81. Okay, so it's 1.8, and h by b is 1.53. So h by b here, this is the curve for the h by b. So here is a 1, h by b 1 and h by b 3 is there. So it will be in between that. Okay, so put this one and put in between those two here. So you can see here we have to take that track. Okay, 1.53. Okay, so in between the third graph or first graph. Okay, at the intersection you can see we can calculate the CF value. We can calculate the CF value, and that is 1.01, 1.05 actually. Okay, or we can take it 1.1. Let's take it 1.1. Okay, and we will go to the define section, load pattern section, and here EQ WX and modify it, and we can take it as a 1.1 here. And okay, and for y direction the calculation will be different. Okay, so let's take it 0.01, and it should be, so here you have to take it 50 and 3, everything should be 111. Top story should be overhead water tank, and bottom story should be plinth here. Okay, include 1.2, and okay, and here I think we have to modify it, it should be plinth here. And okay, and modify it again. So we have to calculate this CF for y direction. So let's come here. Okay, and again click new and take a screenshot. So for y direction, okay, for y direction now we have to like change the position of a or b. Okay, so let's suppose this is our building, and this is height is h, and this will be b now. Okay, and it is in y direction now, and this will be b now, and this will be a now. Okay, and this will, here it went. Okay, 1 minute, and now it is in y direction. Okay, so it is 1 minute. Okay, so I think 1 minute, 1 minute, 1 minute. Okay, so notation will be same. Okay, notation will be same. Notation won't be different. It will be A, that will be A, it will be B, but dimension will be changed. Okay, for y direction, A will be, click OK. A will be 9.43. Okay, and B will be 17.045. Okay, so you don't need to calculate this also. Okay, so let's go to here. You can see A by B is 0.553 or H by B is 0.845. So again, you have to select the vertical one, and and A by B is 0.553. Okay, so you can see H by B is greater than is equals to 1 here. Okay, so I think H by B is not greater than equals to 1. It's less than 1. So we have to take this graph for the calculation of CF. Okay, so let's H. So for A by B, it's 0.553. So put at the 0.553 here. Okay, 0.55, right? So it will be at this location. And for the horizontal, let's, so you can see here H by B is, so for H by B greater than is equals to 1. Okay, so H by B is 0.854. So for this, it's what it is for 0.5. It is 0.25. So I think it will be here. Okay, below this. 1 minute. H by B for less than 1. Okay. Yeah. Okay. Fine. 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 So it will be here. Okay. Below this one. I think it will be here. Okay. Here. Here. Okay, it will be at this location. Or maybe let's take. Okay. Fine. It will be at this location. Or let's take it higher for 1.2. Okay, okay, let's take it for 1.2 for the curve. So you can see, okay, you can take below over there. Okay, fine, it's okay, it's okay. So you can take 1.15. Okay, 1.15 we can take. So here you can see here this for this location. Okay, for 1.2 it will be here. Okay, so for I think for 0.5 graph will be here. So let's for 0.8 the graph will be below that. Okay, so at for this locate for this point we can take it 1.15. Okay, so let's take it 1.15. So go to the define load pattern, click wi and modify, and 1.1.1115. Okay, and okay, and click ok here. So we have successfully defined the wind load and earthquake both. Okay, and let's go to the our presentation. So we have modified the earthquake and wind load. So let's take it stiffness modifiers. So at the time of the earthquake, the moment of inertia, okay, the moment of inertia of the sections of the column and beam will reduce. Okay, and slabs also will reduce. So we are introducing stiffness modifiers for the tension cracks, and we can design our buildings as per like cost. We can design our buildings within the cost, and it will be like cost effective. So that's why we have introduced the stiffness modifiers. And so let's assign the stiffness modifiers for in the building. Okay, so for shear wall there is no shear wall in building. So for beam it is so for let's select the beam, go to the select object type, and let's select the beam here, select the beam, and we'll go to the assign shell frame stiffness property modifiers, and you can see for the torsion it should be 0.01, and is 0.35, 0.351 or 1. Okay, so 0.35 and apply 1 1 and apply and okay. and we will select object type, and then we will select the column, select, go to the assign frame property modifier, and here you can see for column it's 0. 0.7, for 0. 0.7 moment inertia 2 or 3 axis. Okay, so here should be 0. 0.7, 0. 0.7, and apply, and okay. And now we will go to the select object type shell element, that is floor, and select close, and we will go to the assign shell and stiffness modifiers, and for bending it is, for out of plane, bending 1122 or 12 it is 0.25, for in plane it is 1. Okay, for out of plane it is 0.25, and apply, and okay. So we have successfully assigned the stiffness modifiers in our building. Okay, now we will assign the end release. Okay, so to assign the end release, so there is a, the concept behind the assigning end release, it is moment transfer. So what we are doing, we are transferring the moment from primary beam to the secondary beam. Okay, so to assign the end release, you have to select the all story here. Okay, at the left bottom, and select. So for beam for column to column connection, you don't need to assign the end release. Okay, so you here you can see. So for these two beam, we will assign the end release at this location, at uh, not at the column location, other than the column location we will assign, and at the least moment of inertia. Okay, at the least stiffness we will assign the end release. Okay, so because of that, the moment will transfer from that beam to the dead beam. Okay, so what you can do, you can, for the end release, you can go to the assign frame and end release partial and fixity. Okay, so for that you can select these start point and apply. Okay, not start point. So you have to select the end point and apply. You can see the end release assigned to at this location. You have to select this beam also and apply. Okay, you have to select this beam and select the start point and apply. Okay, and for this beam, apply. For this beam, you have to select end point and apply. Okay, and I think all other beams are connected to the column only. Okay, there is no secondary beam. Okay, and I think above, I think everything is fine. Okay, and we'll close it. And now we will merge the divided frames. Okay, we have to merge the divided frame. So you have to select the all story here. You have to go to the plan and plinth level, apply. Okay, so here you can see the frames are divided. Okay, so what you can do, you can merge the frames. Okay, so you have to merge these frames. You have to go to the, yeah, join frame. You have to click the join frame. Now you can see this is a one beam for column to column. Okay, so you have to check for every beam. Here you can see this is one, this is, you can see this is divided, so you have to join this beam. And okay, this is okay, this is okay, this is okay. You can see this is divided. You have to merge this. You can see this is divided, you have to merge this. Okay, okay, this is also divided, you have to merge it. This is also okay, this is okay, right? No, you can see this is not this is also not joined, so you have to join this one. Okay, I think this is also okay. You can see this is also divided, so you have to join this one also. So let's select this. You can see every joint is, you can see the every joint, right? So okay, fine, it's okay. So you have to remove the extra joint from the model. So to do that you have to go to the select object type and select the joint, select all the joints, and you can delete it. You can delete the extra joint. Okay, here you can see at the left, at the left bottom it is 279, and let's delete this. And again you have to go to select and object type and select the joints. Now there is 273. So all the extra joints now deleted from the model. And now we have to assign the slab diaphragm. To assign the slab diaphragm, you have to go to the select object type. Now you have to select the floors here. You go to select close, and you have to go to the assign shell and diaphragm, and you have to assign the D1 and apply and OK. And let's go to 3D. You can see all the diaphragm has been applied to the slabs. Okay. And now we will auto mesh the wall or floor. There is no wall, so we have to automate the floors. So you have to go to select object type. You have to go to the floors, select the floors, go to the assign, go to the shell, and here you have to select the floor auto mesh option. Okay, and you have to select the auto cookie cut, and you have to select the floor mesh. Okay, and we will divide it in the 1 meter by 1 meter uh, slabs for the better results. Okay, so if we divide the walls we will get the better and accurate results, and for the FEM analysis we have to do that and apply and okay. Okay, now we have done that also. And so now what we will do, so now we will assign the response spectrum analysis to the model. So for that we will go to the define function response spectrum, and here we have to choose 1893 and add a new function. And here we have to write is 1893, and seismic zone is 4, that is in Delhi. Building is zone factor is 0.24, importance factor is 1, soil type is 2, response reduction factor is 5. Okay, and okay. And now we will add a new function again, and here we have to convert to the user defined, and here we will write is 1893, and we will write v because we will convert in the we will convert it in the vertical earthquake. Okay, we will modify it. Okay, we have to modify this. Okay, 1 minute. Okay, so let's delete everything from the uh, graph, and we will take 0 and here 2.5, and we will add, and we will also take it 2.5 and modify it. Okay, so from time period 0 to 10 we are taking 2.5 acceleration. Okay, and okay, and okay. And we have to go to the define load cases, and we will add a new case here, and here spec so we will introduce spec x, spec y, or spec z. Okay, so spec x, here we will select response spectrum. Okay, and we will add a new. So the acceleration u1 should be there in x direction, and default should be is 1893, and let's take scale factor 1000. And okay, here we will select this and add a copy of case, and here it should be spec y, and here we will select acceleration in y direction should be u2 and is 1893 and okay. And here again we will add copy of case, and here we will spec z, and here we will take in z direction acceleration u3, and in z direction we will take vertical earthquake and okay, and okay. So what you can do, you can select these three and you can paste, you can drag them at above wind wall. Okay, again above wind loads. Okay, so it will be easy. Okay, eqx, eqy, eqz, spec x, spec y, spec z. Okay, so here what we will do, we will There is, there is load cases: dead load, live load, modal, service, sunken, wall, live, less than, live, greater than. So here what we will do, we will take like drag modal at the above, and we will modify the dead one. Okay, we will modify the dead one, and let's take it dead in the capital letter, and we will add here like every dead load we will add in the dead load case. Okay, and here it should be finish, then sunken, then service, and then wall, and okay. And in the live section we'll modify it, and we will take live here, and here live less than 3, and we will add it, and while live greater than 3 we will add it, and okay. So we have added dead load or live load. Now we don't need service. Let's delete it. We will delete the sunken also. We will delete the wall also. We'll delete the live less than 3. We will delete the live greater than 3. So here in the load cases, we have introduced modal analysis, dead load, live load, earthquake load, static earthquake load, dynamic earthquake load, and static wind load, and okay. So now we have introduced this response spectrum analysis also, and we have to define the load combination. To define the load combination, you have to go to the defined load combination. You have to add default load combination, and you can select load combination from frame design and slab design. Okay, and from okay, that is okay, and okay, and you here you can see every load combination is assigned. Okay, but what we will do, we will change it from this decon to actual load combination. Okay, you can see the load combination instead of you're seeing decon s2, you can see the load combination right here. So for that, what we will do, we will go to the edit, and interactive database. Okay, and here at the load case definition, we can find load combination, select, and okay. So here you can see all the load combination, that is decon s1. So we will change this data. So for that, what we will do, we will select the Excel and send table to the Excel. And what we will do, we will open the another model. So let's do that. So here you can see the results in Excel. Here you can see here, okay, all the results, that is decon s1, okay, from ETAB, the load combination from ETAB. So what we will do, we will introduce our own load combination in this Excel. So for that, what you will do, you go to the edit, you will go to the edit, you will go to the interactive database, and you will go to the load cases, load combination, select the load combination, and okay. Here you can see the name, we can see the actual load combination here. Okay, because if you will assign the decon load combination, there will be a always, there will be a uh, there will be a difficulty to see the results in different load combination. Okay, so always assign these load combination, and you don't need to add load combination. I will tell you one method in which the everything will be assigned by 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 the reference model. Okay, and then you can do anything, you can edit any data. Okay, I will tell you the other method also to select the all the settings already in the new model. Okay, so let's copy everything here from here, and copy it, and I will send you this reference model also, and you will paste all the data. Okay, so let's what we will do, we will select all the data from this Excel, and we will delete the data, and we will paste the data from the table. Okay, you can see everything is here, and now we will go to the this and go to Excel and retrieve table from the Excel. So you can see everything is assigned. uh, okay, every load combination is assigned. Okay, and apply to model, and select, always select no here. Okay, and done, and done. So let's go to define load combination. So here you can see all the load combination is already assigned. So you have to delete the temperature load combination here, okay? Because there is no temperature load in the building. So let's open the load combination, this one, and modify it. So you can see dead load scale factor 1, live load scale factor 1. Okay. So here you can see, let's open this one, modify it. You can see dead load scale factor 1, live load scale factor 0.7. Okay, let's open this one. Okay, let's open this one, modify. You can see dead load scale factor 1.5, EQY scale factor 1.5, and 0.3 into 1.5, that will be 0.45. So spec Z, and that will be 0.45. Okay. So every load combination is correct. Okay, you have to see the whether you have assigned accurate load combination or not, and click OK. So we have successfully assigned load combination in our model. So I think let's go to here, and okay. So now we will assign the fixed support at the base. So you have to select one story here. Okay, please make sure at the right bottom it should be one story. You have to go to the plan, and you have to go to the base here and select every joint from the base, and go to the assign joint, restrain, and fixed support here, and apply, and okay, and go to the 3D. Okay, and now, okay, so there is one thing we have to make sure about. Uh, okay, so there should be no warning in the model. So for that, we will go to the plan plinth. Okay, apply, and you select the all story here, and select the whole model, and go to the analyze check model, and select all. Okay. So you can see model has been checked, and there is no warning in the model, so we can proceed further for the analysis. Okay, and I think, okay, so we have assigned the fixed support. Now we will run the analysis. Okay, so we have prepared our model now. Okay, so we can do the analysis right away, and let's do the analysis right away. So you can see our model is, analysis is done. Okay, now we can see the results. Okay, so we analyze the model. Okay, so we have to match the base shear first. So to match the base shear, I have given you a Excel. Okay, in which you can see these are the scale factor here. Okay, scale factor, you have to match the base shear with using scale factor. Okay, so we will go to the display, show table. Okay, and structure output base reaction, click the base reactions. Okay, and here you can see the EQY, EQZ, spec X, spec Y, spec Z. You can select everything, and okay, copy this, and you have to paste in the Excel at this location. Okay, and you have, I think we have assigned 1000 scale factor. We will go to define load cases, spec X, modify. You can see we have assigned 1000 scale factor for every one for spec X, spec Y, spec Z. Okay, so what we will do, we will write 1000 here. Okay, so this is the scale factor we got. So let's copy this. Modify it, paste here, and okay. No, no, no. In spec X will, okay, cancel it. Modify. Okay, so in the EQZ you have to modify it. Okay, and it should be 0.67. Okay, I will tell you later why we are doing it. Okay, why we are taking it 0.67. You can connect the dots. Always you can connect the dots backward. You can't connect the dots forward. So let me complete every stability checks and every steps in the projects, or what you can do, you can connect the dots backward, and I will tell you all the informations related to the design detailing, and about the codes, which codes we are using, and why we are doing, and why we are taking these methods, and what will be the difference in the results. Okay, and okay, so and okay, let's run it again. Okay, and go to the display, show table, and okay again. Okay, and EXEY spec Z. Okay, and copy this and paste here again. Okay, and it's 1000. Okay, so let's copy this and done, and we'll go to the define, we'll go to the load case, we'll modify the spec X. Okay, and we'll paste the scale factor here, and okay, and this is for X. Okay, 1 minute. So copy and paste. So this is for spec X. Okay, this factor we have to take. Okay, and now for spec Y, we will copy this one, and we will modify spec Y, modify the spec Y, and we will paste here. Okay, and we will modify the spec Z. We'll copy this one and we'll paste here, and okay, and we will run it again. So we will go to the display, show table. Okay, and we have to go to the base reaction. Okay, and you can see, so EQX is matching with the spec X. You can see it's 633 kilonewton, and it's also 633 kilonewton, and EQY is 663, and spec Y is also 663, and EQZ is 4435, and spec is 16. Okay, so here we are, here something is wrong. Okay, something is wrong for EQZ only. For EQX and EQY, we are doing it, we are done it correctly. Okay, so something is wrong with EQX. I have to check it again. Okay, so we'll go to the define load pattern. Let's check the EQX and modify 0.412, 0.24. It's correct. Okay, and let's go to the define function response spectrum, modified 0 to 2.5, 0 to 2.5. It's correct. Okay, and let's go to define load cases for EQZ modifier 0.67. Okay, and okay, okay, and I think it's spec Z, and okay, fine, okay, fine. It's 16769. Okay, so we'll modify it. Load case spec Z, It's 16. It's U3. Okay. It's U3. It's response to school. Okay. It's everything is correct. So we'll go to the define mass source. We'll modify it. We have included the mass, vertical mass also. Okay. I think there is an issue with the calculation, I think. So let's again copy this. So let's run it again, okay? To the display, show table, okay, and EQX, okay, and copy this again. We'll copy this and uh, we will go to the Excel again and we will paste here, okay, and here you can see it should be 999. Okay, it's okay. It's 1 1. It's 226 here. Okay, so we have to change this one. So what we have to do, we have to go to done. We go to define load case spec z, modify it, and we will copy this one and we will paste here. Paste here. So you can see it's 43. So there is a mistake. I think there is a big mistake. Copy this and paste here. And okay, and okay, and we will run this again. For the display show table and okay. So here you can see we have matched the uh, vertical earthquake also. Okay, you can see it's matching with the FX. Okay, so the our main purpose is matching the spec Z with EQZ. Okay, so we are not calculating the reinforcement using EQZ. We are only calculating the reinforcement using spec Z. Okay, so here you can see in the combination, we have not introduced EQZ. We have only introduced spec Z. Here you can see. Okay, so EQZ is just to calculate the base shear in Z direction, and we will match the base shear uh, with using the spectrum in Z direction. Okay, so now we will we have matched the base shear. Now we will we will do the concrete frame design. So we will go to the concrete frame design, and now its design is run by the itself. So you can see there is a lot of frames are failing. So we have to increase the size for that. Okay, you can see here verify all member passed. Okay, you can see 139 concrete frames are failing the design check. Okay, so like if you want to check in which load combination it's failing, so you can see it's failing in decon. Okay, so what we have to do, we have to remove the decon load combination. So we will go to the define load combination. Okay, here you can see there is a decon load combination also. So you have to remove the decon one. Okay. I don't know why it is introduced in that. I don't know why. So I think it's added by software only. And okay. So here you can see from here, uh, we will go to the load combination, select design load combination, and we will select every load combination here and we will transfer it in the design combination. Or okay, so here these are the two load combination. There are service load combination, design load combinations are there. So what you can do, you can select the service load combination and you can paste here. Okay, so there are only design load combination, and okay, and we will do the design again. So there are a lot of serviceability checks we have to check in the model. Okay, first, so you can see there are a lot of serviceability checks are there. So these are, I think, one, two, three. I think there are almost 15 stability checks are there. Okay, so you have to check every stability checks first doing the design. So in the tomorrow session, I will go through the all the stability checks. Right now, I'm just doing the design, and I will show you how you can check the design data. Okay, so here you can see. So there are only less load combinations. I think only less members are verify the. Okay, so only 22 concrete frames are failing. So for these 22 concrete frames, you have to check whether its joints are correct or not, or we can increase the size of the frame. Okay, or we can do some changes in our model also. Okay, so if you go to the plan and plinth and apply, okay, you can see here these beams are failing at the plinth level. I don't know why these are failing. There is some, so we will check. You can see in which so it's failing in spec Z load combination. Okay, you can see here. So it's failing in shear only. Okay, it's not failing in a longitudinal reinforcement. It's failing in shear only. It's not failing in bending. It's failing in shear. Okay, you can see shear steel. There is OS over stress is there. Okay, and cancel. So always you can see the data. Okay, it's in red. So if it's failing in longitudinal reinforcement, it will show you like this. 1 minute. Okay, there is no overstress actually. Okay, so all the beams are failing in shear only. Okay, so let's check these beams in which load combination it is failing. So you can see it's also failing in spec Z. Okay, so why it is different? Okay, you have to merge these two beams. Okay, so the reason to merge beams, it's it will show you the different uh, steels for different beam. Okay, so if you will merge this, it will show you the same steel. Okay, so that's the reason. That's the main reason. Okay, so here you can see. So here you can see we are seeing less reinforcement at this location because we have introduced end release at this location. So that's why it will transfer. So that's why you can see seeing a larger reinforcement at this location. So the moment will transfer to this beam, and we have to provide the large reinforcement at this beam, rather at this beam. Okay, so that's why you have to introduce end release at this section to transfer the moment, and it will show the less reinforcement in this beam. If you won't assign the end release at this beam, so it will show you the large reinforcement at this sections. Okay, so suppose it's 215 here. You will if you won't assign and release, it will give you the results like 1800, 900 like this. Okay, so you can see why it is failing, in which load combination it is failing. Okay, so you can overwrite this also. You can see we are using frame type is ductile. Okay, it's ductile. Suppose we are designing ordinary frame. Okay, suppose let's go to here, and so I think it's a moment resisting frame. We are designing a RCC building with spatial moment resisting frame, and we have taken 5 here. Okay, it's a spatial. So you can see if you overwrite it, it's a ductile. It's a spatial framing. Okay, so if you will take, suppose our building is zone 2 and we have taken response reduction factor 3 here. So you have to change it from ductile to ordinary here. Okay, you have to change it ordinary always for zone 2 building. So our building is zone 4, so that's why we have to take zone ductile. Every frame should be ductile here. Okay. Mhm. So let's come to the stability checks. Okay, so we will go through all the stability checks tomorrow. Okay, so for today it's almost 2 hour session is there, and we have go through all the modeling and load assigned to. We have assigned all the load to the model, and we have modeled the actual analysis model for the analysis and stability checks and for the design. Okay. So from the results section, you can see display beam design, and you can see all the longitudinal rebar and transverse rebar. Okay. Suppose let's go to the transverse rebar and apply. Okay. One, no, it's not that. Okay, 1 minute. Close. It's not that. Okay. So go to the design, concrete, and view revised preference. Okay. So here you can see. So the gamma steel should be 1.15 and gamma concrete. Okay, factor of shading should be 1.5 here. Okay, and everything will be done by the software and pencil. And let's go to design and select design combination view result override. Okay, so steel frame. So go to the display beam design. I think it's display design info and total longitudinal. So you have to select total. You can select this one also. So it will give you the. So you can see all the percentage. Okay, rebar percentage here. If you select the shear reinforcement, you can see the shear reinforcement here. You can see here. So it is showing you over stress here. You can see. So it is failing in shear at this location. Okay.